Let me start recording. Okay, so a couple of bits and pieces. So new reading is up on Carmen. There's a reading quiz coming up. New homework that's due a week for today. The last week of in-person classes. The university just made a change to the spring that the first 2 weeks of classes in the spring will be completely virtual. And the world is going insane. I don't know what else to say. I feel like right now we're pretending all this is normal. The pandemic and our political situation. And man, this is just a hell of a ride. And it's I know it's really stressing me out. I know it's got to be really stressing you guys out. On the upside, providing nothing bad happens, Buckeye hockey starts next week, which will make me, I will breathe a huge sigh of relief. As a huge OSU hockey fan. It's like football is the thing that gets in the way of hockey season for me. So this will be the first time since I've come to Columbus that I haven't had season tickets. So next year, provided life kind of returns to normal, my everyone come hang out with me. I'm in the my seats are in the first row right behind the student section next to the band. I do follow the NHL, but I'm a Sabres fan, so there's not much to get excited about there. Yeah, I know. Yeah, it's been a rough dozen years or so as a Buffalo Sabres fan. How is the Blue Jackets vodka? Is it any good? I mean, vodka is just vodka, so it's not like it has any flavor. Okay, well, let's get started with actual actual science, right? So today, so on Friday, we spent a little bit of time and we went over some transformations in steel, and we talked about on Wednesday some transformations in aluminum, and growth was an aspect of that. Today, I want to dive into the details of precipitate growth a little bit more. I wanted to show you guys this. So this is my copy of Porter and Easterling from when I was an undergrad. And this chapter is like heavily annotated. And I don't understand how I passed this class because I like highlighted everything. So this just sort of makes me remind myself of when all of this material was new to me and how I sort of struggled with understanding what was the important parts too. So I'm going to try and make that, keep that clear as we go through this. So, okay. So let's get started. So if we think about growth, right, we said before that the successful nuclei are going to be those with the smallest nucleation barrier, those with the smallest critical volume. And because of the nature of the Boltzmann statistics, small changes in activation energy really get magnified, right? So really all the precipitates that we see are going to be those precipitates that have the lowest energy, right? We're not going to see ones that nucleate in other places simply because when you plug those in, the nucleation rates are so different. So we can say that essentially the precipitate that we're going to see is really the one which minimizes the total interfacial free energy, right? So in the absence of large strain effects, right? If there is a large coherency strain or a large volumetric strain or misfit, then that elastic energy is going to overtake. But we're assuming here that there's not a big volume change between the alpha and beta phases or whatever phase transformation we have, so that we're really driven by interface effects. Okay. And so the nuclei that we have are going to be have a bounding surface that's a combination of coherent and semi-coherent interfaces, which will tend to be flat facets, and smoothly curved incoherent interfaces. Okay. And so for the precipitate to grow, these interfaces are going to migrate, and the shape that develops during growth are going to be determined by how fast those different types of interfaces can grow, right? And what we see is the coherent or semi-coherent interfaces have the lowest energy, and therefore they also have the lowest mobility. They have the lowest mobility because adding any atoms to the surface is going to cause a little protuberance on it, which means I now have a region of incoherence. So I have a high energy region wherever this is going to be growing. So their growth rate is going to be slow relative to incoherent surfaces that are going to be fast, right? So what that means is that a faceted interface like this is going to grow faster, and coherent interfaces are going to tend to remain planar, and precipitates that have a mixture of growth will tend to form these plates. Secondary phases that have coherent interfaces tend to form these plate-like or needle-like structures, depending on what's on the specific details, right? So let's for a second pretend that this interface here is approximately planar, right? And it's fully incoherent, right? What does incoherent mean, right? It means that there's no atomic correspondence across this interface. So that means that there's a high amount of free volume here. There's a large way that we can accommodate the atoms shuffling around, right? Whereas when we have a semi-coherent or coherent interface, there is an atomic correspondence, right? That means we don't have a significant amount of free volume at this interface, right? So let's pretend we have a region where this interface here is nearly planar, and let's see if we can take a look at the kinetics of how fast this interface is going to grow, right? Okay, so our situation looks like this, right? We're up here in the single phase alpha region. We quench down, we're at composition X naught or C naught. right? And the composition of our beta phase is way over here, very rich in B. The composition of our equilibrium composition of our alpha is here. And just like in solidification, we're going to assume that at the interface, we're at the local equilibrium concentration. So just a tiny differential amount x to the right of the interface, we're at the alpha composition, the equilibrium alpha composition. A tiny little bit to the left, we're at the equilibrium beta composition. So we've got a big change in composition across that interface. And we have a composition profile in the alpha phase, right? That goes from our supersaturated alpha at our equilibrium composition, and we have a gradient that goes down to our equilibrium composition. And just like in solidification, the length of this is going to be determined by how fast we can diffuse B into from out here to our beta phase, right? This composition profile is essentially formed by our beta phase sucking all of our B out of our supersaturated mixture, right? So this is the case here where we have diffusion against a composition gradient, right? We're diffusing from a region that is low in concentration of B to a region that's high in composition of B, right? But we're going with the chemical potential gradient because B is much happier at this point in our beta than it is in supersaturated alpha, right? So even though we're going against the composition gradient, we are going with the chemical potential gradient, right? And we don't want to forget that. So we've got this interface here that's moving at a velocity v, right? And it makes sense, should make sense, that the rate at which this interface can move is going to be completely dependent on how fast we can get B out of supersaturated alpha into beta, right? So if we think about it logically, we can come up with a couple things that we think are going to be in this velocity expression, right? The first being the interdiffusivity of A and B, right? Right, the interdiffusion coefficient. The second is going to be the supersaturation, right? How much of a drop we have here, right? And how big of a change do we have, and how much do we need to move, right? And so that's the difference between the composition of beta and the alloy composition, right? So all of these differences are going to play in, right? And then we can think maybe there's going to be something a little more subtle as well, in that as we keep transforming beta, eventually we're going to reach a limit where our composition of our alpha, overall composition of our alpha, starts dropping, right? When this composition profile gets long enough that it starts intersecting with the field from other beta precipitates. And we'll that's going to change things in a way that we'll see will slow the rates, but we'll pretend for right now that the beta precipitates are well separated so that this composition profile concentration profile can essentially just keep extending out. Okay. So that's our big idea, right? So the velocity of the interface is going to be directly determined by the rate at which B can diffuse from bulk alpha into beta, right? We're going to assume the concentration of the interface is always in local equilibrium, right? So we can say that the velocity, or the change in position with change in time of our interface, is in an exact analogy to our stability criteria for interface growth, right? We had a critical wavelength that was set up by the diffusivity and composition gradient, right? We're going to have something like this, right? We have our interdiffusion of A and B divided by the change in how much beta we have to move through. So this change here, right? And a diffusion, right? This is going to set up that critical length, and change in composition with change in time, right? So if we have a unit area of interface, right, one unit, and it advances a distance dx, we have a volume of material 1 times dx, right? A little slab has to be converted from alpha containing at composition equilibrium to beta containing composition beta moles of B per unit volume, right? So that means we need, there should be a minus here, CB minus CE dx moles of beta have to be supplied by diffusion through alpha, right? So this is what sets up our time and our critical length. Okay, so we can make this, make some simplifying assumptions here, and we'll assume that this composition profile here is linear, and then we can do some quantitative analysis, right? So if we assume a linear composition profile, right? And so dc by dx is what we're going to call delta C naught, right? Which is C naught minus C equilibrium. So this is our alloy composition. This is our equilibrium composition divided by the length, right? Oh, shoot, this got cut off somehow. I changed fonts and I didn't realize it got cut off. Okay. So anyway, so basically what's missing is, as this advances, we have mass conservation, right? So the area of this triangle has to be equal to the area of this rectangle, right? And so we can then plug that in and we get a velocity expression that looks like this, right? And then if we make the assumption of constant molar volume in the two phases, and one more simplifying assumption, that the change in composition from beta to the alloy composition is significantly larger than the change in from composition here, C naught to CE, right? Which means if we go to our phase diagram, that this length, you can't see my fingers, this length here right? This length is much larger than, why isn't it letting me draw? Than this length, right? If that's the case, we can make another assumption and say that CB minus C naught is approximately equal to CB minus CE. If we plug that in, we solve for X and we integrate, right? We come up with these two expressions, right? The derivation of this working through the math is not super critical, right? It's good if you want to do it on your own. What is important is what comes from this, right? So the position, the amount that's grown, scales with the square root of time, right? This is why I say whenever my rule of thumb is whenever I'm thinking about anything that has to do with diffusion, square root dt is the first thing to think about, right? So the position of this interface is going to move with the square root of time, which means what does the square root look like? Right? Meaning it's going to grow fast at the beginning, but as it goes on and on and on, it's going to grow slower. And the amount that it's going to move in a given time increment is going to slow down, right? As we go on. Right? And this is what's called parabolic growth. Okay? The other thing is that the velocity is going to be proportional to delta x naught, which was what we said is this supersaturation, the difference between the equilibrium composition and the alloy composition. Right? So the growth rate is going to be proportional to this, right? It's also proportional to the square root of the diffusivity over time, right? So that means as time goes on, as time gets larger, our velocity is going to decrease. Right? So these are the important takeaways, right? Parabolic growth, right? If our interface is a big flat plane that's incoherent, it's going to grow following the square root of dt. And the velocity is proportional to the supersaturation, and it's going to be proportional to the square root of d by t. Right? Working through the math, yeah, it's good if you do it once, but just remember this stuff. Okay. So we've got two effects here, right? If we look at our velocity, we have a diffusion term and a supersaturation term, right? And our diffusion term is in under this square root. Our supersaturation is here. And so if we look at the diffusivity as a function of undercooling, the higher the temperature, the more diffusivity we have. So this term increases with temperature, or the diffusion term increases with lower undercooling, or the diffusion decreases with undercooling. And our supersaturation increases, right? If this is our alloy composition, as we cool down, our delta x naught gets larger and larger and larger, right? So we have these two terms that are moving in opposite directions. So that means there's going to be a maxima in our growth rate. There's going to be some undercooling that gives us a maximal velocity, right? Because we're always going to be bounded between these two curves, right? So just like nucleation has a maximum velocity as a function of undercooling, so does our growth. Now, the issue is that our maximum for nucleation and our maximum for velocity don't occur at the same undercooling, right? If we're normally, what happens if we're at our maximum undercooling for nucleation, we have lower growth, right? So that means we're going to have much more nucleation and our particles are going to grow smaller. If we're at our maximum undercooling for our maximum velocity for growth, we're going to be less than optimal. We're going to be too hot for large amounts of nucleation. So that means we're going to have a smaller number of nuclei that are going to grow much larger, right? So developing appropriate processing for our materials is getting this balance between undercooling for nucleation and undercooling for growth, right? And the distribution of precipitates and secondary phases that we're going to see is largely driven by this. Okay. As I said before, right, if we have two beta particles that nucleate and they're both sucking B into them, right, into the particles, what we have is a composition profile that eventually they're going to overlap. And the composition, the bulk composition of alpha is going to be leaner in beta over time, right? And as this gets lower and lower and lower, our overall supersaturation becomes lower and lower, and our growth velocity is directly proportional to the supersaturation. So that means our growth velocity is going to slow down as our as our supersaturation decreases with time. Another way of looking at this is as our supersaturation decreases, our chemical potential gradient lowers, right? Meaning that there's less driving force for diffusion. The B is happier here than it was when our alloy composition was out here. So our driving force for diffusion goes away as our bulk phase becomes leaner and leaner in B, right? Given an infinite amount of time, we will have a composition profile that looks like this. But it takes a long time to get there, right? So usually what we see is that we end up with compositions that approach the equilibrium value, but our alpha is still richer in B than we would expect from just the equilibrium phase diagram. Oh, my allergies are killing me today. I took an antihistamine, but I'm still all sniffly, so I'm sorry you guys are subject to me sniffling and itching my nose like that. Right? Okay. So when we talked about steel, spent a lot of time on Friday looking at grain boundary allotropomorphs, both of the cementite and of ferrite. And the reason why the grain boundary allotropomorphs can form so easily is essentially we take advantage of grain boundary diffusion, right? We have a easier mobility, right? And so we can diffuse much faster. We only have to have bulk diffusion from the solute to the grain boundary. And then we can take advantage of grain boundary diffusion to our precipitate, right? And it can grow out this way by interfacial diffusion. If this is an incoherent interface, right, we have interface diffusion between alpha and beta, right? So we can actually diffuse this way and grow much faster than trying to only move bulk beta in from bulk diffusion this way, right? And so it changes our kinetics from what we had before, because our source for our B isn't just coming this way, right? It's also coming along the interface this way. And we have essentially a limitless supply of it because of easy diffusion along the grain boundary. And we have a huge amount of grain boundary surface for bulk diffusion to get us to, right? So grain boundary allotropomorphs can grow much faster than inner growths in the middle, right? So allotropomorphic ferrite will grow much faster than idiomorphic ferrite, for example, or grain or allotropomorphic cementite will grow much faster than idiomorphic cementite. Okay, so what happens if we have a plate or a needle, right? So we talked about before we had a perfectly flat interface here, right? And we said it was essentially can be treated as a one-dimensional case. So that means we had like the growth of a half space, right? So this is all beta back here, and we were worried about how fast this planar interface goes. In reality, we have a very different situation, right? We have a, oh, right, okay, my trusty Zippo lighter. We have a plate like this with a radius of curvature. This is a curved interface, right? And we want to know, and this interface here is coherent or semi-coherent. So it's not going to grow. It's going to grow very slowly this way. This is an incoherent interface. It can grow faster this way. And unlike the planar case where diffusion was only one directional, now we have three-dimensional radial diffusion to this tip, right? So we're not as limited with our source of B as we were before. So that's going to change things. There's also the fact that we now have a radius here, which means that the composition of beta, due to this small radius, has to be considered. We have to consider Gibbs-Thompson effect. So the composition at the tip of this radius is different than what we would have for our equilibrium, right? So we have less supersaturation, right? And to see why, we'll look at the Gibbs free energy curves in just a second. But we also have enhanced diffusion. So it's not immediately, well, I shouldn't say that. We don't have enhanced diffusion, meaning that bulk diffusion is faster. We have diffusion, we have a greater source for beta because we have radial diffusion rather than just one-dimensional linear diffusion. Okay, so that means mathematically this is a much more difficult situation to treat. Okay, but let's just review from Gibbs-Thompson, right? If this is our free energy curve for the beta with a perfectly flat interface, our common tangent means our alpha is going to be at this composition, our beta is going to be at this composition, right? But due to Gibbs-Thompson, our free energy of the beta phase increases with a tighter and tighter and tighter radius, right? Meaning that due to our common tangent, our alpha phase, the equilibrium of our composition of our alpha phase near that tight interface is richer in beta than it would be for the flat interface. And because normally this, if this beta is, say, an intermetallic like cementite, or a stoichiometric compound like in ceramics, what it means is that the composition of beta is going to stay about the same. And we only need to really consider the composition change in our alpha. Again, this is still mathematically a much more difficult thing to analyze mathematically. But essentially, there's a couple things that change. First, our supersaturation is reduced, right? And the concentration, which means the concentration gradient available to drive diffusion, is also reduced, right? And that's because the alpha is happier with a lower concentration due to Gibbs-Thompson. Okay. The diffusion analysis is much more complicated because of 3D radial diffusion, right? But a bunch of smart people have worked it out, right? And it's actually not too hard to show. If this was a graduate class, you'd have to work it out for homework, but for you guys, it's just enough to say that diffusion profile length, this critical length L, is going to be proportional to the diffusivity minus the composition gradient, right? And it all looks the same, but this length here is some scaling factor K times the radius of the tip. And K is going to be about 1, right? It's a little less than 1 usually, but depending on the exact geometry, right? But it depends, the radius factors in there. Okay. We can add a whole bunch of other simplifying assumptions, some additional analysis. Your book gives the ultimate cop-out and just says it can be shown, right? Which is keywords for the math gets really nasty, right? And it's definitely beyond what we need to do for this class. But we can show, you can work through it and show that the change here in our mole fractions, our delta x versus delta x naught, is going to be dependent of the ratio between r star, which is our critical radius for nucleation, and the radius of that tip, right? So when our radius is exactly the same as our critical radius for nucleation, this goes to 0. We have no undercooling, and we have no growth velocity in that direction, right? Right. So it's not growth of a needle or of a plate or a needle. At the very smallest, it's growth, radial growth of a small nucleus, right? It's not lengthening of the needle. But when this becomes larger, when R becomes larger, this will approach the amount of supersaturation that we have. The due to the Gibbs-Thompson essentially goes away, and we're left with X delta. Our supersaturation step equals what it would be in the limit of the planar interface, right? So what we have now here is a shoot, what did I screw up? Dang it. This equation is wrong. What did I type in wrong? I should know it off the top of my head. But that's the way brains work. Hold on. Oh, no, that's right. That's right. I just, yeah, no, this is right. I'm just wasn't thinking right. So what we end up with is a velocity term that looks like this. That's essentially independent of time.
Yeah, what?
Right? And so if our velocity is independent of time, right, it means that the integral of velocity is position. So that means if velocity is constant, our position has to be linear with time, right? Which means we have linear growth. Okay? So the flat interface, we had parabolic growth, meaning that as time went on, the velocity got slower and slower and slower. Here, we have linear growth, meaning that it's just going to keep growing at the same velocity, right? And the primary difference is because we have this 3D radial diffusion. So the growth rate, the initial growth rate is going to be slightly slower due to the undercooling or the supersaturation, but it's not going to slow down. So that means these plate-like precipitates, when things tend to form, they have strongly coherent interfaces. The rate at which they grow this way is going to be much faster. So plate-like and needle-like precipitates tend to be very, very common in our microstructures. Right? So if we extend to needles, really the big difference is the spherical tip of the needle means we have a bigger increase in Gibbs-Thompson. So our value for R star is going to be a little different. Remember R star, one way to view R star, the critical radius, was in light of Gibbs-Thompson. We could think of the penalty for that surface energy, the surface tension that we get, the energy penalty of taking a flat interface and bending it. So our R star values are a little different in that case. but this is a subtlety. We only really considered spherical nuclei when we talked about homogeneous nucleation, because you get essentially all of the physical insight from there. So the trend of linear growth is the same. It's just we're going to have a different sort of scaling out front. Right. Okay.
I got a question.
Sure.
Would go back to the previous slide.
This one or this one?
One more. Keep going. Sorry. One more. Need that. Yeah, that I just need that diagram there.
Okay.
Would the length L be a function of it running into another growth, or as a function of the total surface area that it's now so big that it's not growing as fast? I'm trying to figure out why some crystals are so small and some of them have these big long plates.
Okay. So
does that make sense?
Yeah. So this L here is going to be a function of two things: the difference, the composition change from beta to our alloy composition, right? And it's also going to be a function of this diffusion, right? So that's really what's going to set this up. L is a constant times our radius, essentially.
Okay.
The question of why some precipitates stay small versus why some grow large in different systems, right? That is going to have to do with potentially the nature of these interfaces, how fast, how easy they are to nucleate, right? If you nucleate only a few and I have a good supersaturation, they're going to grow very, very large. If I nucleate a fairly large amount of them and I don't have a very big supersaturation, then each one is only going to grow a little bit, right? Because as this all right, essentially, if we've got a whole bunch of nuclei close to each other, this composition profile are going to run into each other faster, right? And we're going to deplete alpha of B at sort of a faster, at a longer, when the precipitates are much smaller, right? Essentially, it's always going to take the same amount of volume fraction of beta, right, to get us down from our alloy or material composition down to our equilibrium, right? The lever rule sets how much of each material we have, right? It's just what the distribution is. Did we nucleate a whole bunch of small particles? Then each particle is going to grow to a given size, right? It makes sense if we nucleate twice the number of particles, each particle is going to have half the volume to get to the same volume fraction. But if we only nucleate 1/100th, right, then each particle is going to grow to 100 times the volume, right? And if these interfaces are coherent and don't grow wide, right, don't grow slowly in this direction, which essentially tells us that assuming we keep a constant width of this particle, if we have 100, if we have our nucleation is 1/100th means each particle is also going to be 100 times longer. Right? In reality, it'll be like 75 because this interface isn't completely immobile. It just doesn't grow nearly as fast as this way, as it does this way. Right? So the real reason we see the difference between the precipitate sizes comes back to this balance between nucleation and growth a lot of the time. Right? The fact that nucleation and growth have optimal values at different levels of undercooling. Right? Okay, so we will stop there. On Wednesday, I'm going to talk about the growth of coherent and semi-coherent interfaces, and then the JMAC theory, right? And that will essentially finish us up for diffusional phase transformations, right? We'll look at a couple sort of case studies, a couple more case studies, but that's it. And then I still haven't quite figured out on the time that we'll do these last three subjects. I think we might do grain growth and sintering next because it keeps with the diffusion aspects, then do vitrification and crystallization, and then the last topic will be Martensitic transformations, right? And that'll be it for the semester, right? For Martensite, yeah, forged in fire. No, I do want to talk about some of the actual theory of Martensite, the phenomenological theory of Martensite. Right. So, and a little bit about tempering, right? Oh, yeah. So blacksmithing, right? For anyone who's interested, there's still a couple more slots. CDME is running a blade, the TMS, the professional society runs a bladesmithing competition each year. And for the first time, OSU is going to have a team enter, and there's a couple more slots. It's run out of CDME, and I think there's 3 more openings on the team. So if you want more information, oh, Ethan's participating. So if you want to give the information.
Yeah, so can everybody hear me?
Yeah.
Okay. So I work for CDME, and basically my boss decided that he wanted to have us go do this. So it's basically a team of all undergraduate students, or not all undergraduates, all students. And we're making a blade out of a leaf spring is what we've decided so far. So it's going to be 5160 steel, and basically we're going to meet up with an artisan over the course of the next few weeks and have him show us how to make a blade. And then we have a 10-page report due by January 14th, a video and a poster as well. So it's a little bit of work, but you get a published paper out of it, which will be really good for resumes and all that kind of stuff. And it'll be a lot of fun because who doesn't like blacksmithing? Yeah.
So some teams that have done this for a while, no, anyone can participate. You don't even have to be MSc or welding engineering. Some of the teams that have been doing this for a while, like Colorado School of Mines has a big steel center. they're actually this time round. I know the advisor of the team really well. They're going from ore to a blade, right? They're actually digging up, mining their own iron ore, and are going through the whole process that way. So, pretty crazy what some of the groups that have been doing this for a while have done. I'd say sign up, talk to Ethan. Sorry to put you on the spot, but
You're good. I can get you in contact. Just email me. I'll put my email in the chat, and I can email you the leader's email because I don't know it off the top of my head. But yeah, if you're interested, let me know. That's my name.number.
Yeah, so it's,
please email me.
So it's Jake. I can post it up on Carmen too.
Okay.
So I always forget how to spell Jake's last name.
It's Rindler.
Yeah, it's a C, not a. There it is. Yeah. All right. So there's Jake's the advisor. I've been asked to sort of jump in as a secondary advisor, which is how I know that it's happening. I wasn't aware of it at all. But yeah, I mean, you know, the first time doing it, right? These guys, you know, putting in a lot of work to do it this time. So. Okay, well, we're a bit over time. Everyone stay safe out there. You know, you don't want to be bringing anything home with you for Thanksgiving. So stay safe, stay healthy, and enjoy the rest of your week.